A blindfolded subject, when instructed to walk in a straight line, may actually walk in an arc. Humans rely on visual, vestibular, and auditory cues to orient themselves. We are exploring what happens if a virtual environment user is presented with a virtual scene that slowly rotates about them. Will they notice this rotation? In this diagram, the user is represented with a small blue arrow. The user is walking towards the yellow trumpet player, and the user's path is drawn as a white line. Can we fool the users into walking along an arc when they believe they are walking in a straight line? Previous research suggests we can. Here we show a subject walking back and forth along a straight line in the virtual environment. In actuality, they are rotating in the lab, and the result is that the user walks in a star pattern. We conducted a user study to explore this phenomenon. In the experiment, the subject trained for a fire drill in this virtual environment. There were 4 buttons on the walls that the users pushed in order before exiting the room through the doorway on the far wall. This is the path the user followed through the virtual room while performing the fire drill. The dimensions of the virtual room were approximately 20 meters by 6 meters. In comparison, our lab space was 10 meters by 4 meters. How can we present this virtual environment in the limited lab space without being relegated to flying via joystick or some other presence-breaking mode of locomotion? The solution is to cause the user to rotate so that she walks back and forth between the ends of the lab without noticing. We do this by slowly and imperceptibly rotating the virtual environment in relation to the lab at strategically placed waypoints in the task. The 4 buttons on the walls that the user had to push are our waypoints. At the waypoints, the user turns 90 degrees in the virtual environment. These turns are in fact almost 180 degrees in the lab. The user does not notice this because her relatively rapid turning causes substantial vestibular stimulation. Against this high background, the additional vestibular cues caused by our rotational distortion are unnoticeable. Here we show the user's path in the virtual room and what they see in the head-mounted display. Here we can see that as the user zigzags through the virtual environment, they are in fact traveling back and forth between the ends of the lab. Here we show an overhead diagram of the virtual room in blue overlaid onto a diagram of the lab in red. The thick green line at the bottom of the screen displays the subject's real angular velocity. The thinner green graph shows the amount of rotational distortion we are injecting. Initially, the user is lined up to walk from one end of the lab to the other as they walk from the practice button to the alarm button in the virtual environment. We do not need to rotate the virtual environment yet. Just after the user has pushed the alarm button, she looks around to find the next button. Here we inject a large amount of rotational distortion. Now the next virtual waypoint is almost lined up with the waypoint in the lab. We make up the remaining misalignment as the subject walks to the next waypoint by injecting rotational distortion proportional to the subject's linear velocity. This results in the arced paths we see here. In this manner, we are able to present a large virtual environment in a small lab space while retaining the naturalness and high level of presence associated with real walking.